Hello everyone, welcome back to Technologies Discussion channel. For this video, I'd like to continue the discussion on digital communication. This video, I'm going to explain the different types of line coding, okay, which is also known as line encoding. Okay, so in fact, there are actually 5, but for this video, I mainly concentrate on the 3 most popular line coding, which is unipolar, polar, and bipolar. As I mentioned earlier on, let's say there are 5. Another 2 will be the multiple level and multiple transition. So basically, these are the different types of line coding. I'm going to go in depth on unipolar. For example, under this unipolar, I have this non-return to 0. For polar, there are actually more scenario. For example, I have the non-return to 0 level, and I also have the non-return 0 inverted. And there's another one which is return to 0, okay, but this is hardly used. Most of the time, in fact, we will use Manchester and differential Manchester. Coming to my last part, which is the bipolar, okay, so basically I will emphasize on AMI, okay, which is the alternative mark inversion. Okay, so basically all this will be the objective of this video. Guys, okay, so if you have any question regards on this discussion, okay, you can always send an email to me. Okay, so this is actually my email, okay, but okay, I actually prefer you guys to send me through the comment. Okay, I hardly check this email, so it will be better if you can send through the comment. Before I continue, guys, this is very important to me. I'd like to urge you guys to help me by like this video. Give me a few seconds. Press the like button now. For those who are new to this channel, and if you want to encourage me, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. What is line coding? Okay, so you can take a look on this diagram. You can see that line coding, in fact, is actually the process of converting this digital data, which consists of bits of ones and zero, into a digital signal. Okay, so this digital signal can be an electrical signal or optical pulse. Okay, so the key objective is to send from the transmitter to the receiver through a physical transmission medium over here. So basically, this is actually what line coding is about. Okay, so basically for this physical communication channel, they could be a wire, okay, they could be a fiber optics cable or wireless. Okay, so what is a baseband transmission techniques? Okay, so in short, baseband transmission technique means that they actually send the signal without shifting it to a higher frequency band for a transmitter. And when we actually receive it, we don't need to shift them to a lower frequency. So this is a very simple meaning of baseband transmission. In this process, you can see that a bit sequence, okay, so basically these are all the bit sequence. Basically, they are converted into digital signal, okay, using this encoder. So after that, they actually send over a communication channel, okay, a transmission medium, all the way to reach the receiver. Then we actually has this decoder. They actually recreate back the original digital data. So this is a very simple idea on line coding. So there are, in fact, 3 different types of line coding, which I have just explained on the introduction. Unipolar, okay, I actually have this non-return to 0. Polar, okay, basically they have more. Okay, for example, we have this non-return to 0 level, non-return to 0 inverted. This return to 0 is hardly used because they actually supersede by Manchester and differential Manchester. Over here, bipolar, I actually has this AMI, alternative mark inversion. Let me explain the key difference between these 3. For example, for unipolar, let's say my bit is equal to 0. Okay, my time diagram will be equal to 0. Let's say the binary bit is equal to 1, then I will have a pulse. Okay, to be more precise, a positive pulse to indicate a bit of 1 actually sent over. Next, on the polar, okay, basically, let's say the digital data is 0, okay, then I have a minus so-called pulse to indicate. When my bit is equal to 1, I will have a positive pulse to indicate. But this is not really a default. They can actually so-called reformat differently. For example, 0 can be positive pulse, 1 can be minus pulse also. Okay, but you can see the clear distinction over here. you can see that they actually has a minus and positive, but for this case, it's actually 0 and positive. Next, I'm going to move on to bipolar. Okay, for bipolar, when let's say the bit is equal to 0, then I will have a 0 in terms of the type diagram to represent it. When the bit data is equal to 1, then it could be either plus or minus pulse to indicate this binary bit of 1. Okay, so basically these are the different types of line coding. Let me explain the first line coding, which is unipolar, okay, which is also known as on-off signaling. Okay, so why they are actually known as on-off signaling? Okay, because of this concept. So basically, they only use just one voltage level. For example, okay, let's say the message is actually 1. So basically, they have this 1 pulse to indicate message 1 is actually sending over. If let's say the message is equal to 0, they actually has a 0 voltage to indicate message 0. So from here, you can see that basically it's a on-off. Okay, so if the message is 0, they will be off. If the message is 1, they will be on. So therefore, okay, they actually has this name which is known as on-off signaling. One of the example of unipolar will be non-return to 0. Okay, so the level is constant throughout the bit interval. Okay, so let me use the next page diagram to explain this. So for example, this is actually the level. Okay, so basically throughout the bit, the level will be constant. So this is what you want to say. The level is constant throughout the bit interval. Coming to the advantages of this unipolar, they are extreme, very easy, very simple. Okay, basically, if there's 1, okay, it will be positive. If it's 0, it will be 0. So basically, you can see that this kind of circuit, they are actually very simple. Coming to the negative portion of unipolar, okay, basically, it requires DC component. Because if you require DC component, which means that you require power, so hence it will be quite wasteful in terms of the power. Another disadvantage is time synchronization. Imagine if you are going to have a very long string of 0 or 1, then you may have so-called issue in terms of the time synchronization. This unipolar, they are rarely used in today modern long-distance communication. Let me give you further example on this unipolar. Okay, so basically, as I mentioned earlier on, one of the example will be non-return to 0. Okay, let's go a little bit more detail on this non-return to 0. So basically, it's a unipolar line coding scheme. Okay, so basically, very simple. I think the diagram will explain the whole thing. The positive voltage actually define bit 1. Okay, so basically, you can see from here, all the bit 1, they actually has a positive voltage. And when it's actually bit 0, it actually has 0 voltage, as you can see from here. So basically, this is the skin, okay, under the line coding, which is non-return to 0. And I have given you a very simple understanding, okay, by this diagram to understand what is actually non-return to 0. Coming to more information on this method, this skin actually use more power as compared to polar skin. Okay, so basically, as I told you that it requires a DC component and is considered quite wasteful. Let's say, okay, when we actually compare by just sending the 1 bit per line, okay, so this method also require more power. Moreover, for continuous sets of 0 or 1, there will be some issue, as I mentioned earlier on. Imagine that if this is long string of 1, we may be having some issue in terms of time synchronization, or this is also known as the baseline wandering problem. Okay, so basically this is for the unipolar. Let me come to polar, two equal but opposite voltage levels. What does this mean? Let me give you an example to understand this. So let's say if my digital data is equals to 1, then I can indicate by having this plus V over 2 to indicate data 1. So let's say my digital data is equals to 0, then again I can use this minus V over 2 to indicate data 0. So from here you can see that they actually has equal voltage level, but different sign, plus and minus. So this is actually the meaning of two equal but opposite voltage levels. Okay, so under this polar, we have this first one, non-return to 0 level, and also non-return to 0 inverted. Let's come to this first, okay, non-return 0 level. The voltage level actually depends on the bit. Okay, so this is actually very common in early digital system. In short, this is actually quite similar with non-return to 0. Okay, so which I'm going to explain with an example later on. Let's just focus on this non-return zero inverted, okay, which is slightly tedious. Okay, firstly, okay, the transition at the start of the bit interval actually represents a 1. No transitions actually represent a 0. Okay, so let me use my own word to illustrate this 2 point here. So let's say the next bit is actually equals to 1. Then I will have a change in terms of the transition. For example, I can change from low to high or high to low. If let's say my next bit will be equals to 1. Let's say my next bit is equals to 0, then I will not have any form of transition. Okay, so probably if you are still confused, maybe later on I will have an example to explain this. But just keep this in mind. If the message is equals to 1, the next bit is equals to 1, then I will have some form of transition. Either I change from high to low or low to high. If let's say my next bit is equals to 0, then I won't require to do any transition. I just stay put. For example, if it's low, I just stay put at low. Let's say it's high, I just stay put as high. Coming to the advantage of non-return to zero inverted. Okay, so basically they will have a better synchronization as compared to non-return zero level. Okay, let's say that it's a strings of 1. Okay, if you still remember, I told you that if let's say there's a 1, okay, I actually need to do the transition. Okay, so which means that I need to change the state from high to low or low to high. So I will not have any issue if let's say the data is continuous one, because I will have some form of transition. I will not lose in terms of the synchronization. However, coming to the disadvantage, if let's say the number is a string of 0, then if you still remember, I won't have any form of transition. Then again with this, I may have some issue in terms of time synchronization. And then basically DC component is possible also. So as this method belongs to the early days, okay, so basically they are used in USB low speed and magnetic recording. Okay, so nowadays, to be very frank, we don't use this anymore. Before I continue the example of non-return to zero, level, and also inverted, I need your help, guys. Please help me by like this video. Okay, so I just need a few seconds from you. Help me press the like button now. For those who are new to this channel, and if you have learned something from this video, you can always help me by subscribing to this channel and turn on your notification bell. Once again, thank you so much for strong support. In polar skin, okay, so the voltage are on the both side of the axis. Okay, so what does this mean? Okay, so let's take a look on the time diagram of so-called the level and the inverted. Okay, so basically you can see that they are actually at two different axes for this level and also for the inverted. Okay, so basically this is actually the separation between the two axes. So this is actually what it means. Okay, so basically the voltage are on the both side of the axis. Let's come to a little bit more information on the level and also the inverted for non-return to zero. Okay, so these skin are somehow quite similar to unipolar non-return to zero. Okay, but for these two cases here, they actually use two voltage level. But for this unipolar non-return to zero, they only has one voltage level. Another one will be 0, if you still remember. But for this case here, for the level and also for the inverted, they actually has two voltage level, as you can see from this diagram here. Okay, they will appear at two different voltage level. Let's come into more detail. Okay, so let's start by understanding more on this non-return to zero level. Okay, so the voltage level directly determine the bit value. Okay, so basically with the voltage level, I will be able to tell whether it is bit 1 or bit 0. Typically, okay, so a logic high, okay, I actually will have to represent a binary 1, and a logic low can actually represent a binary 0. Okay, but I do slightly different. Okay, so typically, so I didn't do it typically. So basically from here, you can see that, let's say it's a bit 0, I actually has a positive to indicate this. Let's say it's a message 1, I actually has a negative to represent it. So basically from the voltage level, you can see that if it's 0, I'm going to have a positive voltage. Let's say it's 1, I'm going to have negative voltage level to indicate it. So basically, this is for the non-return 0 level, which is quite similar with non-return 0. Basically, for non-return 0, basically they only has one level, the other level will be at 0. Okay, so this is for the non-return 0 level. Let me come to non-return 0 inverted. Okay, so This is slightly complicated, so follow me through to understand this. A transition in the signal level, okay, so from high to low or low to high, occurs at the bit boundary only if the light speed to transmit is a logic 1. Okay, so later on I'll show you a diagram to understand this better. Okay, so let's say if the next bit, okay, basically is a logic 0, then there is no transition actually occur. Okay, before I kickstart on the discussion on this non-return 0 inverted, okay, so we need to take note on this first. Okay, so for the non-return 0 I, okay, inverted example later on, okay, so we assume the signal level before transmission the data, okay, basically will be positive. Okay, so therefore there is no transition at the start. Okay, I come to this again. Okay, at the start, okay, and the first bit 0. Let's come to the time diagram in order to understand this better. Okay, so let's come to the inverted one. So as I mentioned earlier on, let's say the first bit before this thing actually started is actually a logic high. So let's say the next bit is 0, then I don't need to do any transition. So I will remain as logic high. But if let's say my next bit is equals to 1, then I need to change my transition. Okay, I need to change to low now. So next bit, if let's say it's 0, then again, I don't need to change my transition. I will be remaining at 0. Again, the next bit is equal to 0. So I will remain my transition. I don't need to do any transition. So I will be remaining at so-called negative axis here. So the next bit will be equals to 1. Then I need to do some form of transition. Okay, so basically, again, next bit is equals to 1. Then I need to do transition. Okay, so with this, I think you know the meaning of non-return 0 inverted. So basically, the next bit will be important. If let's say the next bit is equals to 1, then I require to do a form of transition. If let's say my bit is equal to 0, okay, so you can see from here, I don't require to do any form of transition. So this is actually for non-return 0 inverted. So let me do a quick comparison between these two methods, the level and the inverted one. Okay, so basically the baseline wandering affect both skin. Okay, so basically you can see that it will affect both skin. Okay, but it is twice as severe in NRZ-L as compared to NRZ-I. Let me come to this. So basically imagine, okay, so let's say if it's a 1, okay, for this inverted, I will always doing some form of transition. So I may not have this effect of baseline wandering. But let's say if it's still a string of 0, then I will have the same effect of non-return 0 level. Okay, so basically this is the key difference between these two. If let's say it's a string of 0, then for this case here, for the inverted, I will have issue. But if let's say it's a string of 1, then I may not have issue. Okay, so this is what you want to say here. Okay, so this difference arise, okay, because use a transition, okay, when the next bit is equals to 1. Okay, so with this, you can see that I actually minimize the issue. Let's say the message is a string of 1. Okay, so basically this is a key difference between non-return 0 level and non-return 0 inverted. The next example of polar will be return to 0. Let's come to the characteristics of return to 0. Firstly, the signal actually returns to 0 voltage halfway through the bit period. What does this actually mean? Let's take a look on this time diagram in order to understand better. Okay, so this simply means that at the half, okay, basically they will return to the 0 voltage. Basically, from here you can see that at the half, they will return back to the 0 voltage. So this is actually for the return to 0. Okay, so as you can see earlier on, you can see that let's say the message is equals to 1. I will be basically changing from the plus volt, okay, to the 0 volt. Let's say the digital data is equals to 0, then I will move from minus volt to 0. Okay, so later on, I will have an example to illustrate this more. Coming to the advantages when we actually use this return to 0, you can see that they actually solve all the time synchronization issue. Okay, so regardless whether it is a string of 1 or a string of 0, you actually totally eliminate away all the time synchronization problem. Coming to the disadvantage, okay, because of this disadvantage, because it requires twice the bandwidth of non-return to 0, because you need to do 2 changes in 1 bit. So therefore, because of this, this is in fact not commonly used for data transmission, because of bandwidth inefficiency. Coming to the example of return to zero. Okay, so one solution, okay, of this non-return zero issue, which is the time synchronization. So therefore, we have this return to zero scheme here. Basically, for this return to zero scheme, they actually has three value. The positive value here, the zero value here, and the negative value here. So basically, this is what you want to illustrate. They actually has three possible value: positive, negative, and zero. Okay, so in this scheme, the signal goes to zero in the middle of each bit. Okay, so in the middle, okay, all of them actually goes to zero, regardless whether it's a message 1 or 0. They will just go back to zero in the middle of each bit. The logic we are using here to represent a data, basically, let's say for example, the bit is actually equals to 1. Okay, so let's take a look on this here. So basically, when the message is equals to 1, you can see that they go from positive, they go back to 0. Basically, this is what you want to say over here. You will go to positive, after that, they will go to 0 voltage. If let's say the message is actually 0, okay, so basically, the message 0, it will go from negative, after that, they will return back to 0 again. So basically, this is on the return to 0. Okay, so basically, I think you have a better understanding now. So let's say it's a message 0. I will go from negative and then return back to 0. Halfway through, I will return back to 0. Let's say it's a message 1, then I will have a higher voltage, the positive voltage. After that, I will return back to 0. Again, let's say the message is equal to 0, then I will have a negative voltage level, and then I will return back to 0. So this is actually for the return to 0. The key thing is they want to resolve the time synchronization. Okay, but because of the so-called twice the bandwidth, this is hardly used. Okay, so the main disadvantage of return to 0 encoding, okay, is typically it actually require greater bandwidth. So another problem is the complexity, okay, because it use three level, okay, the positive, negative, and 0 voltage. As a result of all this, okay, so this scheme is not used today. Instead, it has been replaced by the better performing Manchester and different Manchester scheme. Okay. With this, I'd like to end my discussion. On my next video, I will further discuss on the polar, okay, with the Manchester and differential Manchester. But because I think this video will be quite lengthy if I include these two, so basically look up for my next video. With this, that's all I have for today's discussion. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.